Perfect.
All right. Okay. So, yeah, I want to talk about, well, first, maybe just the formality, I suppose, in this meeting to say what the Bergman projection is, right? But I use P, capital P, the orthogonal projection from L2 onto the analytic subspace. And in this talk, our domains will be bounded domains in Cn, and most of the time they will be smooth, but not always. I want to talk about three aspects. I think one's a priori estimates, what do we know about them? Then I want to talk about duality and estimates. And then I want to add a remark on, just a brief remark on Worm domains, namely it would be nice to exhibit a smooth function, a concrete smooth function with a non-smooth projection. I mean, spoiler alert, I can't do that, but I have what I think is a very good candidate, sort of a natural function whose projection one should try to figure out. And I suspect it's not smooth. All right. So a priori estimates then, well, we say that the projection satisfies a priori estimates in double Fk if there is a constant C sub k, so that whenever both F and PF, that's the a priori part, PF also has to be in double Fk, then there is an estimate that K norm of PF is estimated by the K norm of F. Let's use the notation AK of omega, that's the double Fk intersected with the analytic functions, that's a closed subspace of double Fk. Now we can view the projection, well, of course it's a bounded operator in L2, but we can view it as a possibly unbounded operator from double Fk to AK with the domain, domains of K of P just being those F in double Fk whose projection is also in double Fk. That's then a linear operator, like I said, possibly unbounded. And then it's not hard to see that saying that P satisfies a priori estimates in double Fk, that's the same as saying that this domain is closed. Obviously, if you have the a priori estimates, the domain will be closed. If both Fn's and PFN's are in AK and both converge, right, then because of convergence in L2, the limit F and PF will both be in AK. And the other direction is just a closed graph theorem. If this domain is closed, it's a Hilbert space in its own right, and this operator then does have a closed graph that just follows from continuity in L2. And so then it's continuous, right? Which means these estimates. All right. So let's look at some non-pseudoconvex domains. And of course, we want to look at some domains now where we know that actual estimates fail. And the first family, countable family of such domains was constructed by David Barrett in 84. He has smooth bounded non-pseudoconvex domains in C2, omega j, so that whenever P is greater than 2 plus 1 over j, then the smooth compactly supported functions are not mapped into LP. So in particular, right, if you take J big enough, you see that for any P greater than 2, there is going to be such a domain so that the image of C infinity 0 of omega j is not contained in LP. Nevertheless, though, for each j, the Bergman projection on omega j does satisfy a priori estimates in double Fk. And this is for all k starting at 1 and then all the way up to infinity. This was proved by Harold Boas and myself in 1992. what happens is that if analytic functions on an omega j have just a little bit of extra regularity, a little bit better than being in L2, and being in sub F1 suffices, then these functions have to extend to a bigger set. And this happens in such a fashion that the boundary parts of omega j, where you have trouble proving actual estimates, get swallowed up by this extension. And we use then methods that we had developed for domains with symmetries and so forth, to get estimates on sort of the remaining boundary parts. But the estimates are just a priori estimates. But nonetheless, at the time, that was kind of remarkable, and certainly showed that one has to pay attention to the issue of turning a priori estimates into genuine estimates. This is maybe even more so in connection with the phenomenon operator than with the Bergman projection. One often proves a priori estimates first, and then you're not done really. These have to then be turned into genuine estimates. Now, a few years, well, just a couple of years later, actually, Barrett and Fornes gave an example of a domain. Well, it's more than one domain. It's, in some sense, it's also a class of domains, smooth bounded Hartogs domains in C2, so that A infinity omega, that would be analytic function smooth up to the boundary, that space is not dense in the Bergman space. And so in particular, then the projection cannot take sub left k to sub left k. In fact, cannot even take C infinity of the closure into A infinity, right? Because otherwise you take an analytic function in the Bergman space, you approximate it in L2 by functions smooth up to the boundary, then you project, and if those projections were in A infinity, you would approximate in L2 by functions in A infinity, because the convergence in L2, of course, is preserved under the projection. Now, as far as a priori estimates for these domains is concerned, they sort of fall into two subclasses. On one subclass, we can prove a priori estimates. On the other subclass, we cannot. And well, what are the two subclasses? Well, first, let me explain a little bit what these domains are. You start from the Bergman domains, where you wind just a couple of times, and then instead of capping off at the top, you connect down again to the bottom. And you can do that so that of the circles, the disks rather, that you wind, only finitely many of them have radius 1, the others have a smaller radius. For those, one can prove a priori estimates. Then the others, where you have radius 1 of the disks that you rotate, that you on some open interval in for mod W, you get a critical annulus, and you face sort of the same issue that you have on the Bergman domains. For those, a priori estimates are open, as far as I know. So the general status, as far as I know at least, is that it's an open question whether or not the Bergman projection on a smooth bounded domain must always satisfy a priori estimates. And I think it, having an answer to this question would certainly deepen our understanding of the projection. And what would deepen our understanding, of course, is not the answer per se, but the process of giving the answer. Now, I want to look briefly at some implications for the Bergman kernel for smoothness, or rather lack thereof. Namely, there's an observation of Ligotska dating back to 1998, when you have a smooth bounded domain whose Bergman projection satisfies a priori estimates in sub F k for all k, but fails to map C infinity of the closure to itself, then that is bad news for the Bergman kernel. Namely, if you look at the points, let's see, this looks like I forgot to write something here. Yeah, let's denote by capital V the set of those points. Oh, I've written it up here, I'm sorry. Let's denote by capital V the set of those points where K dot C is smooth on the closure. And then another piece of notation by H minus infinity, I denote the space of harmonic functions in omega, which are in some sub F minus K for some K. So then if we have a domain that satisfies a priori estimates, but the projection is not actually regular, then the idea is that the Bergman kernel for most points C is not smooth. Namely, there exists a harmonic function in H minus infinity, non-trivial harmonic function that vanishes on the set of points C where the kernel is smooth, right? So the idea is that set of C's where the kernel is smooth is a small set. Namely, it's small enough so that you can have a non-trivial harmonic function with somewhat controlled boundary behavior at least, or at most, sort of polynomial blow up in the boundary distance, so that such a function vanishes on this set. So, like I said, this was an observation of Ligotska's in 1998. The proof consists of 4 fairly simple steps. Denote by Q, see the harmonic Bergman kernel, that is the reproducing kernel for the harmonic Bergman space. Then it's easy to see just from the reproducing property, if you project this kernel, you get the Bergman kernel for every point C in omega. The second observation is, well, the harmonic Bergman kernel is smooth for all C, smooth on the closure. Okay, so when I take a point C in V, then the projection of Q dot C is smooth up to the boundary. And because we have a priori estimates, then if I take the closure of this span in C infinity of the closure, then the projection is continuous on this span, mapping into A infinity. Namely, any function here in the linear span is a function where both the function and the projection are smooth up to the closure. So the a priori estimates kick in. And so if you go to the closure, you end up still being continuous mapping into A infinity. All right. The next observation is, well, the closure of the span, of course, these are all harmonic functions in H infinity, harmonic functions smooth up to the boundary. The span cannot be all of H infinity. Why not? Well, the harmonic, the analytic Bergman projection is view it as first doing the harmonic Bergman projection and then following up by the analytic projection, right? Now, the harmonic Bergman projection takes the infinity of the closure to itself, so maps into H infinity. So if this closure were all of H infinity, then by the second point here, the projection would then actually project H infinity into A infinity, and so the Bergman projection, and so would project C infinity of the closure into A infinity, but by assumption that is not the case. So then this is a genuine subspace of H infinity, right? And so there is an element in the dual, a non-trivial element in the dual that vanishes on this whole subspace. And now, when you use duality between H infinity and H minus infinity via an L2 type pairing, which I will explain in a moment, this produces a function in H minus infinity, which, when you pair it in a generalized L2 sense with anything in here, in particular for any point C, with the kernel, with the harmonic Bergman kernel at C, gives 0. Well, because this is a generalized L2 pairing, this harmonic Bergman kernel paired with this function H minus infinity still reproduces the function. And so the upshot is that we now have this function in H minus infinity, which is non-zero because it's a non-trivial element of the dual, which is not identically 0, therefore, but vanishes for all these points C and V, and this is what the claim was. So if you have a domain where we have a priori estimates, but the projection is not actually regular, then the Bergman kernel sort of is non-smooth up to the boundary for most points. All right. So now let me come to, oops, sorry about that, come to duality. And we'll now explain this generalized L2 duality pairing. So let's start with an integer k, a g smooth up to the boundary, and f a harmonic function in sub F minus k. And I define this integral tilde of hg bar. This is defined to be a limit as epsilon goes to 0 of integral omega epsilon hg bar. What's omega epsilon? That's the subset of omega where the boundary distance is bigger than epsilon, as usual. Then there's no problem with this integral, right? Because g is smooth anyway, and h is a harmonic function, is smooth inside, so this integral exists. What is not obvious is that then the limit as epsilon goes to 0 exists, but it does. And the reason is the following. Look at integrals not over omega epsilon, but over the boundary of omega epsilon. Then this harmonic function in h minus k has distributional boundary values, meaning its restriction to omega, to the boundary of omega epsilon, when you transport this to the boundary of omega in the usual way, as a distributional limit. The g, of course, converges in C infinity, these boundary, and so the upshot is that the integrals over the boundary of omega epsilon of hg bar have a limit as epsilon goes to 0, and it is then a corollary that this limit exists. And importantly, this generalized L2 integral satisfies a generalized sort of sub-F inequality, namely the absolute value is dominated by the minus k norm of f and the k norm of g. All right. And now, because C infinity of the closure is dense in sub F k, I can extend this pairing just by continuity to assess collinear pairing on H minus k cross omega k, cross WK, right? This, the idea of such a generalized pairing, this goes back to Steve Bell in 1982, and then in this form, I introduced it in this form and used it in 1984. Okay, it's not that old. It's 1984. All right. Well, it turns out for some of the things I'm about to say, I don't need really the space A minus K. I need the closure of the Bergman space in A minus K, and I denote this by a subscript CL for closure. Namely, in a general domain, the Bergman space need not be dense in A minus K. It is dense if the domain is pseudoconvex. That was proved also in the around 1984 by Bell and Boas. But in a general domain, it doesn't, of course, need not be dense. So we just take the closure of the Bergman space in I minus K. And now I define a map, J sub K, from A K of omega into the dual of this space. And the functional JK of F should act on a function H in I minus K, in A minus K closure in this fashion, integral tilde HF bar. As a map in F, this is conjugate linear. I set it up in this fashion, will be convenient. And if you look by this estimate up here, right, if F is in sub Fk, then this functional has norm no more. Of course, the F with the G up here. This functional has norm here in this dual of no more than the K norm of F. So this embeds AK into the dual of A minus K closure. Okay, so now let's see how this duality sort of is intertwined with estimates. Well, we have the following proposition. Part A, the Bergman projection maps sub Fk to AK if and only if JK is surjective. This is due to Bell and Boas, and then the version with this pairing I introduced, I used also in 1984. Whereas P satisfies a priori estimates in sub Fk if and only if JK has closed range. For the second part, I don't know actually that this is written down somewhere, but anyway, if you look, this is what happened. What happens, I should say. So let me just to sort of illustrate how this duality works. Let me show you how to prove part B, but the direction from left to right. So we assume a priori estimates. We have to show that JK has closed range. So we have to take a sequence in the image, in other words, a sequence of functions Fn in AK, so that JK of Fn converges to some functional tau in the dual of A minus K closure, right? And the Fn's are in AK. Now I want to extend these two functionals on all of sub F minus K, and the sort of an easy way to do this is, I mean, this is a subspace. A minus K closure is a subspace, a closed subspace of sub F minus K. So I can just take the orthogonal projection S, and then I just compose the functionals with S star, right? Oh, this star is in the wrong place. This should be a superscript here. Then S star JKFN will then converge to S star tau, because S star is continuous and will converge in sub F minus K, which I identify sub F minus K star. Okay, I really got half of my stars messed up here. This star here should be a superscript S star. And the convergence here is not in sub F minus K, but in the dual of sub F minus K. Okay, there's a star missing here, which I identify with sub Fk0. And I identify it maybe not in the usual way, but in a conjugate linear way. So I just put a bar on the functions in the pairing. So then let's see what this means. I mean, this is ultimately where our F is going to come from. let's take a function in the Bergman space. From the S star JKFN, we have functions Hn in double if K0. So like I said, the identification here, I take the conjugate pairing. So I'll look at the integral Hn bar G. Then, by the way, we've set this up. This is this functional applied to G, but this comes with S star. So we apply JKFN to SG, but SG is G because G is in that space onto which we project. So then, and the functional JK of Fn acts on G via, well, it would be generalized pairing, except the Fn is in AK and G is in L2. So that coincides with usual pairing. But what this tells us now, if you look here, left side equals the right side, this tells us that the projection of Hn equals Fn, right? Because G is an arbitrary Bergman function. And because now we have a priori, so now for the Hns, we know both the Hn and the P of Hn, which is Fn, is in AK. So the a priori estimates kick in. And so since the Fn's, which are P of Hn, converge to some P of H, then I call this F in AK, right? So I have, right. And so now it's easy to check that tau is just the JK of F. Don't want to go into the details. All right. So that sort of, shows you how much space there is in some sense between a priori estimates and actual estimates. Let me just do a couple of, well, probably just one consequence of this on Barrett's domains, where we have a priori estimates but failure of actual estimates. Well, this means what then? Because we have a priori estimates, JK has closed range, but JK is not surjective, so this means this range can't be dense, and so it's a genuine subspace of the dual of A minus K closure, right? And so that means there is an element, in A minus K closure on which all these functionals in the range here vanish. And when you write down what this means is, this means there is an H in A minus K closure, so that JKFH is 0 for all F in AK omega. And this pairing is just this generalized L2 pairing. So integral F bar H equals 0 for all F in AK. So notice here, both F and H are analytic, but H is not in L2, it's only in A minus K. And so this can actually happen. Although at first sight, this is just mildly counterintuitive, I think. But you can have non-trivial elements in H minus K so that this pairing degenerates. Now, if this cannot happen, it doesn't mean that you have estimates. If you go back here, it just means that you have if that can't happen, it just means that you have a dense range, but you may not be surjective. Of course, if you know that you have a priori estimates and this degenerate pairing, this pairing cannot be degenerate for a non-zero function, then you get the estimates. But just from the fact that there's no non-zero function, so that you have this degenerate pairing, you can't deduce estimates. Now I want to give an illustration of why this sort of duality point of view is useful. And it's something that Catherine Gallagher, Jeff McNeil, and myself observed a number of years ago, 8 years ago. If we have a smooth bounded domain and the Bergman projection maps sub Fk to sub Fk or to Ak for some fixed k, then, and that notation is a bit unfortunate, this is not a closure here, this is conjugate. So conjugate of the Bergman space, in other words, conjugate analytic functions in L2 get mapped to Ak. So this is, if you will, a smoothing property that the Bergman projection has on conjugate analytic functions, well, provided it is regular in sub Fk. Now, this is just one of the things we observe in this paper. We have other smoothing properties which take a little bit more work to prove, but this, I think, is sort of a nice illustration of the use of this duality point of view. So the projection maps conjugate analytic functions to sub Fk functions, and with an estimate, of course. The K norm of Pf is dominated by just the L2 norm of F. Now, the sort of key to the proof here, in addition to duality, is the fact that the scale of negative sub-F spaces of analytic functions can also be described by scale of that measures the blow up with respect to powers of 1 over the boundary distance. So more specifically, the minus K norm dominates here the supremum of the modulus of f of c times the boundary distance to the power k plus 2n, where n is the dimension of Cn. In turn, this dominates a weaker negative sub-F norm, namely the one with index minus k minus 2n minus 2. This is not really hard to see. You use mean value properties of analytic functions and so forth. So now let's let G be a conjugate analytic function, and let's H be an analytic function. And I want to prove something about the Bergman projection of G, namely I want to prove that it is in sub Fk, right? Assuming that P maps sub Fk to Ak. So I'm pairing G with Bergman function, so integral over omega Hg bar, and I've written that 1 here because of the following. Well, notice G is conjugate analytic, so G bar is analytic, so Hg bar is an analytic function, right? And we had further up, we had this duality estimate for this generalized integral, but in our case, the generalized is just the usual integral with this norm, the analytic function minus k norm times the k norm of G. So now I'm going to apply this where the index k is replaced, minus k is replaced by minus k minus 4n minus 2. It's the minus k minus 4n minus 2 norm of this analytic function times the k plus 4n plus 2 norms of the smooth function 1. That's some constant, whatever. Okay. And then I use this left inequality here. This is no more than the sup of Hg bar times boundary distance to the power k plus, and then I write the 4n as 2n plus 2n. And this now is no less than the sup of h times d to the k plus 2n, which is dominated here, if you look at the right inequality, minus by the minus k norm of h, times the sup of modulus of g times d to the 2n, which if you look up here is dominated by the zero norm by the L2 norm of G. So the upshot is this pairing here with my G fixed, as far as H is concerned, is actually continues in the minus K norm. And so because we have estimates sub F K to sub F K, everything in the dual of A minus K, well, closure of the Bergman space in A minus K is in the image of JK. So there is an F in AK, so that, well, first of all, I should say, so this extends to a functional tau in A minus K closure star with norm less than the L2 norm of G, right? But now that tau is JK of some F, we have closed range of JK. So and it's easy to see that JK is injective, so it's actually in this case an isomorphism. So the K norm of F is dominated by the norm of this functional, which is dominated by the L2 norm of G. And so then it follows then that HG bar, that's tau of H, that's JKF of H, that's integral HF bar for all H in A0. And so it follows that the projection of G is actually equal to F, which is in AK, and also the K norm of that projection, it's just the K norm of F, which we saw to be dominated by the L2 norm of G. And that is what the claim was. So it's a very simple proof using this duality. And then of course the other ingredient was this observation that the scale of negative subtle spaces of analytic function can also be described by the scale where you measure the blow up in terms of the boundary distance. All right. So I want to mention one more aspect of this question of a priori estimates, which I once thought this would be really good to try to prove a priori estimates, but it's not so clear. So we look at P sub Fk to AK, and what's the domain sub K, that is those functions in sub Fk whose projection is in AK. Well, every such function can be written as, well, a function in AK, namely its projection, plus a function in sub Fk intersect with the L2 perp of the Bergman space, right? And it's easy to see that the sum is direct. That is, the intersection of these two spaces consists just of zero. So the question is, so we have these two spaces, and both AK and this here are closed subspaces of sub Fk. And so the question then is, when is this direct sum closed? And it's a lemma from functional analysis. If you have a Banach space, even, well, we have Hilbert spaces. If you have a Banach space, X and Y are closed subspaces of C with trivial intersection, then the direct sum is closed if and only if the two respective unit spheres, Ex and Ey, have a positive distance. So here, I first thought, well, it shouldn't be too hard to prove, right? Here are analytic functions. These are things orthogonal, of course not orthogonal in WK, only orthogonal in L2. That's a problem to analytic functions. Surely one should be able to prove that these unit spheres stay apart. This is not, it turns out, the answer is no, this is not clear at all, that basically you're led back to the original problem of the a priori estimates, unless one has some new ideas here. Right, yeah, let me just stick to that. There are some new ideas needed here, showing that the unit sphere in AK and unit sphere in that orthogonal complement stay a positive distance apart. Finally, another question I would like to raise, even though I have nothing to offer in terms of insight, but I think it is an intriguing question. Suppose we just have global regularity, that is P maps C infinity of the closure to C infinity of the closure. Well, what that means in terms of sublet spaces, right? This just means for every K1, there exists some K2, well, bigger than or equal to K1, so that P maps sublet K2 to sublet K1. Whereas exact regularity says for each K, P maps sublet K to sublet K. And so the question is, you know, can you have global regularity, but not exact regularity? Or in other words, can you have global regularity with lots of derivatives, right? You go sublet K2 to sublet K1. This is open. One thing that's easy to see just by interpolation, if this laws were bounded, say if you could always do that so that K2 minus K1 is less than some constant independent of K1, then by interpolation you would find that actually P would map sublet K to sublet K minus epsilon for every positive epsilon. But all of this is open. You know, if you look at it from perspective of the de Bonhoeffer operator, then you look at differential operator, and there are differential operators where you have regularity with loss of derivatives, but for the de Bonhoeffer operator and sort of equivalently for the Bergman projection, this is open. I think it would be interesting to see what's going on here. Then come to my remark I mentioned, but the Bergman domain. So I've written here. I mean, I'm sure you've seen this yesterday in Dave's talk. Bergman domains where we have these disks centered at the point minus e to the I log mod w squared of radius 1 minus phi log mod w squared. Where phi is at n equals 0 on an interval of length 2 beta minus pi. And phi is chosen so that, you know, the domain is smooth and pseudoconvex. So in other words, phi plus phi double prime should be non-negative, and where phi passes through the value 1, the derivative should be non-zero. Then you get the smooth cutoff of the caps. The first sort of indication that things could go wrong here came from Chiselman in 1991. He took Bergman domains but with the caps removed, and he showed that C infinity of the closure is not preserved by the projection. Then breakthrough came in 1992. Dave Barrett showed that actually on the Bergman domain sublet K is not mapped to sublet K, at least for K big enough with respect to the winding. And then finally, 4 years later, Mike Christ used Barrett's result by essentially proving a priori estimates, not quite, I'll comment in a minute, but to then conclude that the closure is, C infinity of the closure is not mapped to C infinity of the closure on the Bergman domains. And in the meantime, Harold Powers and I had shown that if you wind just a little, if you can squeeze in an integer k, or k equals 1/2, you know, below this number, then you will be regular from sublet K to sublet K. Now, the way that the reason we have an integer here, k equals 1/2, this is probably due to our method of proof. If one uses microlocal estimates here, one can probably have this for all s less than this. And there are other results also that go in this direction. But the question I want to, or the fact I want to briefly point out, is in Christ's proof, he actually considers the space of functions that have the property that when you rotate that, when you rotate by e to the I theta and consider the pullback of the functions, they get multiplied by the e to the I j theta. So they sort of look like this: A of c and mod w times w to the j. Where here, of course, this is not analytic. And intersect with sub k, then he shows, well, for all s outside a discrete subset, but that's not so important. There are constants c of sj, so that if both f and pf are smooth up to the boundary, then we have this a priori estimate. But this constant depends on s and j, and even if you fix s, there is no known bound for the csj in j, as far as I know. Now, this is good enough to then use Barrett's results to obtain a contradiction, if assuming that the Bergman projection is regular on the worm domains. But as far as I know, the actual a priori estimates are still open. And lastly, I promised here is sort of my candidate for a function that whose projection should not be smooth. Well, what's a function that sort of you think of at first when you think of an analytic function on the worm domain that sort of exploits the wormness, if you will, the winding? You take log c, right? Now, of course, that's not independent of w. It's only locally independent of w, so it's log c mod w bar. And I take the conjugate of that because, as I've said, if the projection were regular, the conjugate analytic function would have to be mapped into sub k in for all k, so it would have to be mapped into a function smooth up to the boundary. And now it turns out for this particular function, you don't need this general fact that conjugate analytic functions would have to be mapped to the infinity of the closure. Namely, well, suppose you pair a conjugate analytic function with an analytic function, and so you integrate over omega. Well, if you fix w, you're integrating over a disk, so you might as well precompose the Bergman projection with the Bergman projection on each disk, right? Now, if you have a conjugate analytic function on a disk, its Bergman projection is constant, namely, and it's just the value the function has at the center of the disk. If you just take the Taylor expansion at the center of the disk, conjugate everything, then all the terms other than the constant term are orthogonal to analytic functions. Well, so what this means then is the projection of this conjugate analytic function g is the same as the projection that I get when I just on each disk, I take the value at the center. So, well, the log is going to be I log mod w squared, but it's conjugate, so it's minus I log mod w squared. But here, there is really also minus 1 here, right? The center is a minus that, so there is a e to the I pi, which comes with a minus. So this function now is smooth up to the boundary. And question is now, the question I want to pose is the projection of this function smooth up to the boundary or not? Of course, the plus pi here plays no role. Constant, adding a constant isn't going to change things here. Now, if you do remove the caps, then it follows from Chiselman's analysis that indeed the projection of this function and therefore the projection of G is not smooth on the closure. And just to close, some of you may know there is a 201 paper by Straube, which sort of extends Chiselman's analysis, but it's not for general phi. You have to, the phi there, he has to sort of construct, not even construct, it's basically prove that there exists a certain phi so that he can control what's going on the caps. So that is not, you know, won't do this for general worm domain where you just assume on phi what you need to assume to assure pseudo-convexity and smoothness. So yeah, I think it'd be worthwhile to look at this function and see if one can figure out what the projection is. Of course, one can play this game further here. This is now just depending on W. So now if you fix the C, you'll be integrating here over a bunch of annuli, and you can figure out, what that projection is on an annulus. And I think what you get, I haven't done the computation, but as these annuli, go up, and you approach the critical annulus, you get very bad boundary behavior. So that there is yet another function whose projection is the same, but who has bad boundary behavior. So it's certainly believable that the projection might end up with really bad behavior either. Okay, thank you. That's all I have to say.